Greetings! Welcome to Electronics 2. This is lecture number 44 and I am Razavi. Today we will continue to look at the problem of instability in negative feedback circuits and see what condition we exactly need to meet in order to ensure that a loop is stable and does not oscillate. But before we go there, let's just review what we covered last time. We looked at this generic negative feedback system and we said, let's suppose that the feed-forward amplifier has some poles and zeros, so it has a transfer function, so we call it H of S. And the closed loop transfer function of the system is now given by this expression. And then I considered of a special case where the input is a simple sinusoid coming at some frequency omega 0. So I said if the input is just a simple sine coming in here at the frequency of omega 0, then what happens? Well, because we are dealing with only sinusoidal signals here, we will replace S with j omega 0 as shown here, and this is the overall transfer function that we have. And now it is possible that for some value of omega 0, this kh of j omega 0 is minus 1. If that happens, then this whole closed loop transfer function goes to infinity, which means for a very, very small input amplitude, we will still get a very, very large amplitude at the output. And we say the system is unstable and it oscillates. Okay. So, the critical conclusion that we drew last time was that what really happens is this H of S has so much delay associated with it, so much phase shift associated with it, that the signal that goes around the loop is actually inverted as we start from here and we end up here. So we have one inversion because of H of S, and then we have another negative sign here, so the overall feedback becomes positive at this frequency. And that's really the reason for this oscillation. And if you remember, we wrote this equivalently as the magnitude of kh at j omega 0 is equal to 1, and the phase of kh at that frequency is minus or plus 180 degrees, it doesn't matter. So what this tells me is that the phase shift associated with this loop here, right, is 180 degrees. So as I start from here and I end up here, the signal is flipped vertically, so that causes this overall positive feedback. Okay? We thought we designed the negative feedback system because we thought this times this was positive and this was negative, and that's how we arrived at this transfer function, while there's a k missing here. But what happened was that H of S, the feed-forward amplifier, is not ideal. It has some poles and zeros, so it delays the signal, and as a result, it makes the feedback positive at this frequency. All right, so we saw that feedback is positive, and that's why it oscillates. And then we naturally concluded that to make sure the system is stable, we have to avoid this condition, right? So we have to avoid this condition at all frequencies. If at any frequency this holds, then the system will oscillate at that frequency. All right, so I would like to add a few more interesting and important points before we go on. So let me add some more points here. Okay, so the first point that might be obvious, but I need to emphasize is this, that if the open loop system satisfies kh of j omega 0 equals -1, then the closed loop system is unstable. So it's important not to confuse these two. When we say k times h, k is the feedback factor, and h is the transfer function of the feed-forward amplifier, right? So k times h doesn't relate to the closed loop system yet. It is, you can consider it as the loop gain, as we talked about last time, or loop transmission. So we can say that, yes, I broke the loop here, I run around the loop, and I found k times h. Okay, so k times h is a property of the open loop system, right? The loop is broken. We found k times h, and we analyzed it to see if something like this can happen, right? And if it does happen like this, then it is the closed loop system that will oscillate, right? Meaning that after we close this loop and we have an input here and an output here, then the system will oscillate. So these are two different things and must not be confused with one another. Okay, number 2. So the second point I wanted to raise was that even if x equals 0, the system still oscillates if we have this condition of kh of j omega 0 equals -1. All right? So we don't actually have to have this x here. Even if I have 0 here, this will oscillate, provided that this condition holds. I won't go through the details exactly here, but there's always some noise or some other conditions inside here that will make the system oscillate. All right? So in other words, if you're trying to build an oscillator, we don't have to have an input for it, right? You can just build this loop, guarantee this condition, it will just burst into oscillation. Okay, number 3. The third point was, what we want to study is this. What happens if, so remember these two conditions which are equivalent to this? Now let's play a little bit with these two. So if I have this condition, but for this condition it's actually something else. So what happens if the magnitude of kh of j omega 0 is greater than 1, and the angle is still, the phase shift is still 180 degrees. Okay? Now, This doesn't tell me exactly what happens, right? Because it seems that, well, the denominator doesn't really go to 0, so how should I think about it? So we want to go back to this equation and treat it. It's a little more complex than that. But from the perspective that we studied last time, we can still see that such a system, the closed loop system, is still unstable. Okay, so let me show you why. All right, so here's the picture that we drew last time. In fact, when we were studying the stability in the time domain, right? So we said that, okay, I will apply a sinusoid here at frequency omega 0, and I would like to see what happens. So remember, we took different snapshots of this at different times, and we saw that when this was equal to 1, this signal went around the loop, came back here with the same amplitude, but flipped. Then we subtracted it from here, from the input, so we got a larger signal. That larger signal went around the loop, got flipped. We subtracted it from the input, we got even a larger signal, and so on. So the signal went around the loop and became larger and larger. But now we are saying that this magnitude of this loop gain is greater than 1. So what happens? Okay, well, let's use a different color to see. All right, so this guy comes in here, and now it travels through H and K. And the magnitude, meaning just sort of the gain from here to here at this frequency, is greater than 1. But the phase shift is still 180 degrees. So we do flip the signal, but the amplitude arriving here is larger than this amplitude and this amplitude, right? So this will be larger. Now if I subtract this feedback signal from the input signal, I will get something even larger, right? So this will come even larger, and this will just circulate around the loop and will turn into oscillation. So we see from this simple description that even though the magnitude is greater than 1 for kh, we still have an unstable system. Sorry, I have a cough here. Okay, so the key point here is that we should also avoid this condition, right? So it's not just that this should not hold, these two should not hold, or this should not hold. So what we should really avoid is actually something like this, right? Similarly, so this has to be, we must avoid this, whether it's equal to 1 or greater than 1, right? We'll have oscillation as long as this phase shift is 180 degrees. All right? So that's the key point that we need to have. Okay, number 4. Point number 4 is that K usually has no phase shift. So we decided in the past that K is typically 1 or less, right? But also K doesn't have poles and zeros in most cases. Remember, we had just a resistor for feedback or a resistor divider for feedback, so these don't have much phase shift. In other words, what happens is that the angle of K times H is actually about the same as the angle of H itself, because this guy doesn't have any phase shift, right? All the phase shift comes from H and not from K. All right, it just simplifies things, so it's good to remember that. Very well. Okay, so these were a few points. Now I would like to go back to Bode's rules, which I mentioned last time, and just review those carefully with some examples so that we are comfortable with applying Bode's rules to both the magnitude and the phase of any transfer function. All right, so let's go back to Bode's rules. So we looked at Bode's rules for the magnitude in the frequency response discussion a long time ago, but now we're looking at Bode's rules for phase construction. So here how it goes. It says if we have a pole at omega p, then the phase of h, so h is the transfer function and omega p is a pole of that transfer function. Then the angle of h experiences a change of minus 45 degrees at omega p and minus 90 degrees at approximately 10 omega p. All right, so all this means is that if I'm plotting the phase of a transfer function, when I reach the pole frequency, I have to go down by 45 degrees. And when I reach 10 times the pole frequency, I have to go down to minus 90 degrees. And we begin to feel the effect of this omega p at about 1/10 of omega p. So for a single pole system, it looks like this. So let's say you have a single pole. So we identify 0.1 omega p and 10 omega p is omega, okay? And we construct both the magnitude of the transfer function, any transfer function you have, right? Doesn't matter where it came from, whether it's for this or not. And so let's say something is just a low pass filter, right? So it goes like this and it goes down like this, right? That's for the magnitude, as we have seen in the past. The 3 dB bandwidth is here. Now for the phase, you can see that the phases are all negative from the poles. So we write the phase like this. And it says right under the pole, we have a contribution of minus 45 degrees. So minus 45 here. And then at 10 times the pole frequency, it gets to about minus 90 degrees. So minus 90 degrees here. Okay? So at very low frequencies, the pole contributes nothing. It's not there, right? So I have no phase shift. At 1/10 of the pole frequency, we begin to feel it. So we begin to feel it. Go down here, minus 45. And then at 10 times the pole frequency, it's approximately minus 90. Not exactly, right? It would be only at infinite frequency where the phase will reach minus 90 degrees. But at 10 times omega p is approximately minus 90 degrees. All right, so that's for the pole. For the zero is the other way around. So if we have a zero at omega z, then angle of h experiences a change of plus 45 degrees at omega z and plus 90 degrees at 10 times omega z. 10 times omega z. Okay, so let's say there's a system that has a single zero. Okay, we just have a zero. So here's a zero, omega z, omega. So I will plot the magnitude and the phase. Okay, so in this case actually it's positive, but so let me clear this up a little bit. Okay, I need to shift this down so that I have more room for my plot here. Okay, and this is the angle of H. So we follow Bode's rules, right? Bode says when you reach a zero frequency, the magnitude will have a positive slope of 20 dB per decade. All right. So now if you have only a zero, what really happens is that we start something like this. No, sorry, not like that. Let me do it like that. Okay. This electronic board is a little slow today, but we'll get through it. Okay, so this is our zero frequency, and what we know is that the magnitude at this point will want to increase its slope by 20 dB per decade, right? All right, so then if we have something, for example, like this, then it would want to go up by 20 dB per decade. All right, okay. All right, and then for the phase, Bode says that, so let's say we have no phase at very low frequencies, and then we begin to feel it at 1/10 of the zero frequency. So if this is 0.1 omega z here, and then 10 times omega z here, you can imagine that this is a log scale. So around here we begin to feel it, we go up, and we have plus 45 degrees at this point. And it reaches approximately plus 90 degrees at 10 times the zero frequency. So this would be up here, go like this, plus 90 degrees. It's a little messy, but you get the message, right? So we just have to remember these two sets of rules, and it's very easy to deal with any situation. Okay, so let's go to the next page and look at some examples of how we construct Bode plots for different systems. So here's an example. Suppose I have a two-stage amplifier, okay? Just like this. A two-stage amplifier, a simple common source stages. And there's some capacitance here, some capacitance here. Don't worry about other capacitances. I'll call this R1, C1, R2, C2. And we would like to construct the Bode plots for both the magnitude and the phase of the transfer function of the system. All right, I have only two poles. Okay, so here's how it goes. So this is the magnitude of H as a function of omega. At very low frequencies, the capacitors are out of the picture. We just have the low frequency gain of the circuit. And that would be GM1 times R1 plus GM2 times R2 if we neglect channel length modulation. All right, so that's the low frequency gain right here. So we'll write GM1 R1 times GM2 R2. Okay? All right, now we go on until we reach the first pole. Which one is the first pole? It doesn't matter. Let's assume R1 C1 gives us the first pole. So here's the first pole, 1 over R1 C1. So we go until here. And then we deflect by minus 20 dB per decade. That's from our studies in the frequency response discussion. Okay, and we continue until we reach the second pole. So second pole could be here. And now we have to go down by another 20 dB per decade. So this would be minus 40 dB per decade. All right, okay. In practice, for these to make sense, when you say this is dB per decade, this is dB, this is decade. So this should be a log scale. the horizontal axis. And the vertical axis also has to be log scale. So it's 20 log of this. Okay? So the result is in dB, in decibels. But that's how we would do it precisely if we really want to get this to be 20 dB per decade and so on. Okay, now how about the phase? So we plot the magnitude, the phase of H. All right, so we have two poles. We identify the pole frequencies, and we know that right at this pole, we have a contribution of minus 45 degrees. At 10 times this pole, we have minus 90 degrees. At this pole frequency, we have minus 135, because this has another 45 degrees of contribution, minus 135. And then eventually, we'll have minus 180. Okay. Suddenly, this pen decided to act up a little bit. So minus 180 degrees. All right, so we'll do it very carefully, very slowly. At very low frequencies, these capacitors are open, there's no phase shift. So the phase shift is 0. At 1/10 of the first pole frequency, we begin to feel the effect of that pole. So the phase begins to change. At the pole frequency, we have a change of minus 45 degrees. At 10 times this frequency, we have reached approximately minus 90 degrees. So, like this. At 1/10 of this pole frequency, we begin to feel it. So we begin to change. At this pole frequency, we have another change of 45 degrees. So we reach minus 135. And at 10 times this pole frequency, this guy gives us minus 90. We already have minus 90 from this, so we get minus 180. So we get minus 180. All right? Now, of course, what happens here, it depends. So if 1/10 of this pole is lower than 10 times this pole, then this gets merged into a narrower band, or it might become even smoother and so on. Doesn't matter. But the whole idea is how we plot these things once we know the pole and zero frequencies. Okay, so this is an amplifier that I buy, a feed-forward amplifier, an open-loop amplifier. If I place this in a feedback loop, will the system oscillate? Okay, so remember we're looking for this condition. K H of j omega 0 equals minus 1, which equivalently translated to, so actually we replace this with magnitude of kh of j omega 0 equals 1 or greater than 1, right? And then angle of kh of j omega 0 equals 180 degrees, right? So let's look at these two conditions very carefully. We have also the greater, but don't worry about that for now. And we're curious to see if this amplifier placed in a negative feedback system could cause oscillation. This amplifier has only 2 poles. Okay, well, let's see. Let's go and see this condition. What's going on here, right? Can this happen here? Now, we said K usually doesn't have phase shift. So the phase of KH is the same as the phase of H. And I have plotted the phase of H, the phase of the feed-forward amplifier, right? The standalone amplifier. Can this phase ever reach 180? Now, minus and plus are the same. So can this phase ever reach minus 180? And the answer is no. Minus 180 happens only at infinite frequency, right? Because when you have only 2 poles, each of them contributes minus 90 only at infinite frequencies. You can see that from here. So if I have 1 over 1 plus s over omega p, So the phase is calculated as, so angle, so let's call this G of S to avoid confusion. So the angle of G is given by minus tan minus 1 of omega over omega p. How did I do that? I replaced S with j omega, and then I said the angle of this complex number is equal to hyperbolic tangent minus 1 of the imaginary component divided by the real component. The imaginary component is omega over omega p, and the real component is 1. And then this is in the denominator, so I guess a negative sign. So you see that this phase can reach 90 degrees or minus 90 degrees only when this goes to infinity. So only for omega going to infinity. So for any finite omega, the phase of this two-stage amplifier cannot reach 180 degrees. So when we place this in a feedback system, in a negative feedback system, that system cannot oscillate, right? Because we can never meet this condition. So that's good news, right? With a two-stage amplifier, it won't oscillate, provided that the two-stage amplifier has only 2 poles. Very well. Let's move on to another example, or rather an interesting situation. Okay, so I want to now try to articulate what we call the stability condition. All right, this is nothing new, so we have said a number of times that if we want the system not to oscillate, we have to make sure that this condition or these conditions do not hold at any frequency, right? Then we can guarantee almost that it doesn't oscillate. Okay, but let's look at this again more closely, just so that we're comfortable with the idea. I want to show you 3 different scenarios, and then we decide which one is the condition that we need. Okay, so here we go. I will plot the magnitude of kh as a function of frequency and the phase of kh as a function of frequency. All right. So we said the magnitude must not be 1 or higher when the phase is 180 degrees, right? So if you pick any frequency you want, at that frequency, we must not have both of these satisfied. Or if this is greater than 1 and this is 180 degrees. So here's an example to see whether this system is stable or not. Okay, so here's very simple. I have a plot. I don't plot the rest of it. I just plot it right here. Okay. We call this the 0 dB axis. 0 dB, meaning that the gain, this value is 1, right? Because I'm plotting, remember, 20 log of this. So when this 20 log reaches 0 dB, it means that this magnitude has reached 1. So let's say this happens at some frequency. We call that omega 0. And the phase at that frequency also happens to be minus 180 degrees. So it's also omega 0 here, and this phase is minus 180 degrees. Okay, so I bought an amplifier. I assume some k, whatever you want, maybe 1, right? And then h belongs to the amplifier. I can construct this frequency response. It has some stuff here, we don't care. We just go and see where the magnitude is crossing a value of 1, meaning 0 dB, right? And it's some frequency. And then we also plot the phase of that transfer function. K really doesn't have a phase, so it's just the phase of the open loop amplifier. And we see that at some frequency, which happens to be the same, the phase also passes 180 degrees. Is the system stable? No, because that's exactly these two conditions, right? So the system is unstable. So let's write here unstable. So what's interesting is that to test for stability, we're not even looking much around here, right? At these frequencies. We're not looking at the magnitude, what it does. We're not looking at the phase, what it does. We're just looking at somewhere around here where the magnitude is approaching dangerous levels and the phase is approaching dangerous levels. In fact, the more important point is that the phase is approaching dangerous levels. So I want to give you a second scenario. In the second scenario, I have this. So again, I say magnitude, but remember this is always 20 log, right? And this is also log scale. So again, I'm looking at near in this vicinity for both phase and magnitude, so phase of kh. So now let's suppose something like this happens. So I have a phase of minus 180 degrees, minus 180 degrees at some frequency, so we'll call this frequency omega 1, and at that frequency the magnitude is greater than 1, so we are right here, right? So remember, this is 0 dB, 0 dB means 1, so what we have here is greater than 1. Is the system stable? So the phase shift at this frequency is 180 degrees. The magnitude at that frequency is greater than 1. That system is not stable. Remember, among the important points that I wrote on the previous slide, one of them was that. I didn't prove it, but we just accept that if the, let's see here, what happens if the magnitude of the loop gain is greater than 1 and the phase is 180 degrees. And we saw that as it goes around, it blows up, so it still oscillates. All right? Okay, so that condition also leads to an unstable system. So this system is not stable. So we'll write here unstable. Okay, so now we consider the third scenario, and hopefully that scenario is stable, right? So let's see. Here's, again, the magnitude as a function of omega, and then the phase as a function of omega. And this time I'm assuming the following. So at some frequency, the phase reaches dangerous levels, minus 180 degrees. Okay, so minus 180 degrees. And we call this omega 1. Okay? But at that frequency, the magnitude is less than 0 dB, less than 1. So it's something like this. So this is omega 1. At this frequency, the magnitude is less than 0 dB. This is the 0 dB level. Is the system stable? Yes, it is stable. You can see that, you can think of it this way. Where the phase is 180, the loop gain is less than 1. So when we circle around the loop, it doesn't blow up. Or you can say where the gain is 0 dB, the magnitude is 0 dB, the phase shift is not 180 degrees yet, right? So either here, you can sit here and say the loop gain is not enough for oscillation, or here say the phase shift is not enough for oscillation, right? Either of these. So the loop simply does not oscillate at any of these frequencies. So in this case, the system is stable. And naturally, that is the scenario that we want to uphold when we are looking for stability. This is the situation. Now I need to give some names to these things so that from now on we can use those names. The frequency at which the magnitude becomes equal to 1, here or here or here, is called the gain crossover frequency. So, gain crossover frequency. It's just a name. Okay, so here or here or here. The frequency at which the phase crosses 180 degrees is called the phase crossover frequency. So here's omega 0, here's omega 1, here's also omega 1, right? So this frequency right here is called the phase crossover frequency. So these three scenarios gave us three different situations for the gain crossover frequency versus the phase crossover frequency. Here, they are coincident, they're equal. Here, the gain crossover frequency is higher than the phase crossover frequency, right? So you call this maybe omega 2 to avoid confusion with omega 1. And in this case, the gain crossover frequency is lower than the phase crossover frequency. So, for stability, what we need to guarantee is that the gain crossover frequency is less than the phase crossover frequency. Okay, so that's the condition. So anytime we have an amplifier or something, we're trying to see if it's stable or not, we have to look for that, right? If it's not stable, then we have to work hard to bring it to this condition. So if it looks like this, it's unstable, I have to work hard to bring it to this condition. If it's like this, I still have to work hard to bring it to this condition, right? So that is the stability condition that we want to implement in any negative feedback system. All right, so let's look at some examples. So, okay, so we're going to look at a single pole system. So imagine that I have a simple common source stage, and I'm going to use this in a negative feedback system like this. So X goes in here and Y comes out of here, and this is K. So the feed-forward amplifier is just a simple common source stage. All right, and I want to see if this system, let's call this R1 and C1, if this system could be stable or not, right? Okay, so no problem. So again, remember, the way we are thinking about this is that K times H, so that's like the loop gain, when you break the loop and find the loop gain, right? K times H must be studied from the perspective of these, or from the perspective of these pictures here. So we construct these plots for that system and then decide whether the system is stable or not. We need this condition to hold, right? We need that condition to hold. So not that difficult, right? Here we go. Okay, so K. So let's just say for simplicity K equals 1 in this example. So KH is just H itself, right? And again, remember, this is always 20 log. And then omega here. All right, so H is this guy by itself, right? I don't even need to worry about anything out here. So this is a simple common source amplifier I bought. I know how to deal with it. It has a low frequency gain of GMR1, right? Not minus, because this is magnitude. And then it has a pole at 1 over R1C1. And then it goes like this, right? Eventually, this will hit 0 dB right here. So this is 20 log of that. Okay, let's construct a phase profile as well. So here's the phase profile. So it's really, you can call it KH or H, doesn't matter. A K doesn't have a phase shift anyway, so it's just KH, angle of KH. And then we know that at the pole frequency, we will have a contribution of minus 45 degrees. So we start out at zero frequencies. At zero frequencies, capacitor is open. There's no phase shift here. And then over here we have minus 45. And then we go, and at 10 times this frequency, so 10 over R1C1, it's approximately minus 90 degrees, right? It's actually asymptotically approaching minus 90 degrees. Okay, so can the system become unstable? Meaning I have constructed this for H, K is 1, and now I place H into this negative feedback system, and I'm wondering if it becomes unstable. No, because this condition can never be met, right? We can never get it to a phase shift of 180 degrees. So that's always stable, right? So we say always stable. Okay, so a one-pole system is always stable, and that's great news. We also saw that a two-pole system is also always stable. So then when you have a three-pole system, there might be difficulty, right? And that's what we will study next time. I will see you next time.